All right, I'm going to change a little bit about this example. This is a numeric example. So we've already done the algebra example. We've done two graphical examples. And now I'm going to take a look at using the table, which is your numerical example. I do want to add this. We're going to have a moving body along a line. If you prefer, we'll call it a bug. We like to have bug problems. And let's say it's moving along a line smoothly and continuously. And the reason why I'm adding that in is because I want the position function to be continuous. And I also want the position function to be differentiable. That's where the smoothly part comes in. There's no cusp or corners or anything like that on there. And the other thing that I want to add in is I want to do a couple of different things for this. The first thing I'm going to add is that I would like to first talk about displacement. How do I use the table to calculate that? Let's do displacement from 1 to 1.5. So that problem, and again, it's knowing what displacement is that displacement is your change in position. So it's the position at 1.5 minus your position at 1. Your only difference is you're using the table to get that. So we would pull our 36 minus 30.2. And let's assume that this is a calculator problem, and you would just go ahead and type it into your calculator and get your 5.8. And the units of that would be feet for this problem. And then I might come in and I might ask you to calculate the average velocity from 1 to 1.5. And again, that one you would have to know what formula you're supposed to use. What are you doing? That's going to be our displacement, s of 1.5 minus s of 1 over our change in time, which is going to be, and again, you got to show a difference quotient. So I'm going to do 1.5 minus 1. And again, assuming this is a calculator problem, we already did our displacement. So our 5.8 divided by 0.5 is going to give me my 11.6. Now my units on this one, this is going to be feet per second, right? Displacement is feet, time is seconds, so we put that in. All right, so I could ask you to do different things like that on the table as well. Sometimes we might ask you to use the table to estimate the velocity, the instantaneous velocity that you're looking for, like here. So I want to basically get an estimate for s prime of 0.5. Now let's talk about what our options are here. Now notice it asked me to estimate. It did not ask me to find the exact value. It asked me to estimate. These are exact values. This is the displacement. This is the average value from 1 to 1.5. So they're specific values that I have calculated. I'm trying to estimate the instantaneous velocity, and the only way that you can do that is by looking at your average velocities for these values. Now let's take a look at 0.5. I actually have 0.5 in the table and I know the position. And then I look and I see that I have exactly a half away this way, half a second later, I've got this value on this side. I could use these values and calculate the average velocity for 1.5 to 1. I also have as an option, I can calculate the average velocity from 0.5 to 0 or 0 to 0.5 and use that as an estimate. Or you could do kind of what your calculator does and use the go from 0 to 1. That's your symmetric difference quotient, because I do have this equally spaced across, and that secant line, remember this idea is that what we're looking at, or let's be a little bit more cognizant of the data that I have here, that this data, you're at 40, you're at 35, you're at 30.2, it's coming down. So we can use the secant line before, we can use the secant line after, we can use the secant line through the two endpoints. So they're all different options that you can use. I think for this one, I'm going to go ahead and just do the symmetric difference quotient. So you again show what you're going to do. I'm taking S of 1 minus S of 0 over 1 minus 0. And that's going to give me approximately, if I do 30.2 minus 40, usually you do go ahead and get it from the table over my 1, which is approximate. And we're assuming this is a calculator problem. So if it rounds, you would round. If it doesn't, you would just go ahead and get that. So it'd be negative 9.8 feet per second. Same kind of idea here, you know, when you go at 2.7, again, let's take a look at that. I've got the before, I've got the after, I can do the symmetric, but kind of in looking at this, 2.7 is closer to the 3. So the symmetric difference quotient would be more for 2.5. So I would probably go ahead and use this and do the tangent line that's after it because it's a little bit closer when you do it. And again, we'll say our estimate as we're looking at it, I would say S prime of 2.7 is approximately showing labeling it. And then I come in and I do using these values. So we would do our S of 3 minus S of 2.7 over 38.2 minus 45. You do want to get into the habit. I always do end minus beginning because then that top is going to be the displacement when we're looking at it. So, oh, and I just made a mistake, didn't I? Take that out. 3 minus 2.7. So we would have our 38.2 minus our 45 over 0.3, which ends up being approximately, for that one, thought I had it on the paper, oh, negative 22.667 feet per second. So we can have that down, and again, you're going to put your units. I would also take a look at our last one here. We've got 3.5, and 3.5 is not even anything on the table. So pretty much your only choices are going to be for your estimate of the instantaneous rate at 3.5 is going to be to use values where 3.5 is in between. So I would kind of go for those values. So we'll do S of 3.6 minus S of 2.7 over my 3.6 minus 2.7. And when you are, oh, sorry, 3. Making all sorts of errors on this one. S of 3 and minus 3 there. So, and in calculating that one, this actually ends up being approximately negative 37 feet per second. So you get that calculated. Now, I want to add another follow-up question to this one because I want to kind of point out some of the use of those existence theorems as well. So what if I ask the question, okay, so this is 1, we'll call this one was 2, let's call this 3. What is the min number of times that the bug changes directions? Move me up here, changes direction, and then we'll justify because, you know, they're always going to want to put that on there. Now, taking a look at it, let's see what we can do. I mean, we've got this data table here, and let me just clean up some of my work. And we want to take a look at this data table and kind of be like, what can we guarantee? This is why this is an existence theorem. So we want to be able to guarantee how many times it changed direction. Well, all we know is the position, so let's kind of take a look at this. From here to here, we're going down. Now, does that mean that it actually went down the entire time? Not necessarily. It might have gone up from 40 and then down to 35. We don't know that, but we definitely know that it went down sometime in here. We know that from here, again, sometime in there it was going down. We know that here, sometime here, it was going up or increasing or moving left or right, you know, whatever we're doing, decreasing, decreasing, increasing. Then here, 36 to 48, we're increasing here again from here to here. Then we're back to decreasing, 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 and then decreasing. So just kind of in the gut feeling of taking a look at it, if I was saying, how many times did I change direction? At a minimum, because of this decreasing and increasing somewhere in here, I would say there's at least one here, somewhere in here, and then increasing, increasing, decreasing somewhere in here as well. So the answer that we're going to say is that the min number of times the bug changed direction, I would say at least 2 times. But now the justification that you're going to get is something that you're like, okay, what can I use to justify? And you have to use one of those existence theorems. Now, when you're talking about changing direction, now let's talk about when do we know that we've changed direction? We know that the bug changes direction when v of t, the velocity, is equal to 0. So what I'm trying to get is places at where that velocity is equal to 0. I also want to get places where the velocity changes sign. V of t changes sign. Because you might not know exactly where the velocity is 0, but if I know that the velocity has changed sign, and I'm smooth and continuous on my position function, then by IVT, you must have gone through 0. So kind of some reasons that we might give for this in using these existence theorems is the first thing that we could do is we can use the mean value theorem. All right, so the mean value theorem applies because I have a function that is smooth and continuous. My position function is smooth and continuous. So it is continuous and differentiable. And notice that we have calculated several average rates of change here. Remember, the mean value theorem says that if you have a smooth and continuous function, and then that there exists a time, f prime of c, where the instantaneous rate is going to be equal to the average rate that you calculate. So basically looking at this, I've calculated many of these average rates of change that I have here an average rate of, I did the average rate up here at the beginning, let me get myself out of the way, of 11.6. And, you know, I actually picked these for a reason because I wanted to pick things that would help us out. Here's an average rate of 11.6, and that's between 1 and 1.5, right? So that shows that you had somewhere in there, the instantaneous rate had to be positive. Somewhere the instantaneous rate was positive because at some point in the interval 1 to 1.5, the instantaneous rate was equal to the average rate by the mean value theorem. Okay, so that's number one. I can use the interval before that we calculated to estimate at 0.5. I did between here and here, and we got this negative 9.8. So somewhere between 1 and 0, there exists an instantaneous rate at which the instantaneous rate was negative 9.8. So it's negative. And so clearly, since the velocity changed sign from negative to positive, that would be time number 1. And then after that, let's pick this one here at 2.7. We're back to a negative for our average rate, and that's from 2.7 to 3. So clearly, I went from a time instantaneous rate somewhere in there by the mean value theorem would be negative 22.667. So I know that my velocity has changed sign from being negative to positive to negative. And that's going to give me the guarantee by the mean value theorem that there are 2 places at which the bug changed direction. I don't know what 2 places they are, but it definitely changed direction at 2 places. I am going to ask one last question before we leave this and get this in, is that then what if, could I, using this table, determine what is the max position or max value of the position function? So could I use the max value of the position function for the bug? Can I use this table of values to definitively say what the max is? Like we've got, you know, taking a look at your actual position, what we have here is we have that the position, you know, you're at 40, you went down, then you increased and you increased, and we increased to that 48.2, and then we went back down again all the way to the end. So we increased to 48.2, and then we went down again. Can I say that that's the absolute maximum? And the answer to that is no. Remember, we don't know what happens before or after this. It might have left this 48.2, went up, and then came back down to the 45. So the answer to this is we don't know. This is an unknown quantity, we do not have enough information to tell. All right, so that will end up example